Welcome to the fifth lecture of week 1, that is characterization of collection of particle part 2. If you remember the lecture 4, that is characterization of collection of particle part 1, where we have discussed the particle size distribution based on screen analysis. Now once I am having the particle size distribution data, we have represented this in a tabular form. Now in this particular lecture we will discuss how to represent the particle size distribution data in graphical form. So that can be represented on x axis and y axis plot, that is 2D plot. On x axis we will consider particle size and on y axis we will plot mass or mass fraction. How many other ways we can represent this is, if I consider particle size on x axis and cumulative mass fraction on y axis. Further, if I consider particle size on x axis and cumulative volume fraction on y axis. So, by these three means we can represent particle size distribution data graphically. Therefore, the distribution can be reported either in terms of frequency, that is differential form, or by cumulative, that is integral form. To explain how we mathematically represent the distribution data, we will consider the table where we have shown particle size distribution data. If you remember, this is the table where we have shown average size, that is D average, which is computed by considering the arithmetic mean of sizes of screens used in that fraction, and M1 is the mass available on that particular screen. So, here we have the data from screen analysis, and we can represent this in graphical form considering that is particle size, that is diameter D average, and the mass available correspond to that D average size. So, here I am having the value of D average 1 and M1 we can put on y axis. Now why I have written D average farthest, because if you remember the data which we have shown in this table, the topmost has the highest opening. So, it would have the largest aperture size, it will have the largest value, and as we keep on moving downward, the size of particle will keep on decreasing. So, obviously D average will fall farthest in this graph. So, considering value of M1 and D average, we can show the data, we can plot the bar chart for this. So, here if you see this graph, here I am having the value of D average which we have drawn farthest, and considering this M1 and D average we can plot the bar, and similarly we can plot the bar for other fractions also, and then we can write the values of diameter as well as fractions. So, here if you see this graph, here on y axis we have represented this in terms of mass. If I want to represent this in terms of mass fraction, then obviously its nature will not be changed, only the value of y axis will change, which I have shown in this graph, which we called as normalized graph. So, here instead of mass we can consider mass fraction, rest of the things will remain same. So, this is basically the differential form, or we call it frequency chart for particle size distribution. If I draw the cumulative graph, we have to add all mass fraction to get the cumulative mass fraction plot, as we have shown in this table. In this table, if you consider the first column, that is all D average value we have written, and here I am having the mass fraction. So, if I consider the lowest value, that is the minimum size of the particle, and if it has the fraction x5. So, correspond to D average 5, the value is x5. If I consider D average 4, here I am having the value x4 plus x5, because we are making the cumulative from bottom to top. Now, why we are doing this from bottom to top? Because if I consider this D average 4, it means if I consider this opening, the mass correspond to this opening, that is x4, and mass below to this all will be pass from this. Therefore, we can consider correspond to D average 4 the total mass which is the summation of x4 and x5, and we have represented this with capital X4. So, if I want to draw the cumulative plot, on x axis we have represented the diameter and on y axis we can represent cumulative mass fraction. For d average 5 correspond to x5, we can have the bar chart like this. If I want to draw for d average 4, we have to join x4 as well as x5 together. So, correspond to d average 4, we have x4, capital X4 value, which has x5 as we have shown correspond to d average 5, and x4 would be added over here. So, correspond to d average, total mass fraction would be capital X4, and similarly if I consider for d average 3, the cumulative mass is x3, x4 and x5, summation of all these will be called as cumulative mass fraction correspond to d average 3, and in similar line we can write for other fractions also. Here you see. So, once I keep on accumulating from bottom to top, when I reach to the top correspond to x1, the value should always be equal to 1. So, this we call the cumulative graph. If I do this and if I join the center of these bars together, we can have the cumulative plot like this. So, this is basically the cumulative plot. We will use this curve for the computation purpose in subsequent lectures, but here you should understand how to plot the cumulative mass fraction curve. Now, here in this slide I have shown how the particle size and shape is measured, though we have already discussed this, but whatever we have discussed, that is the manual effort. If we want to compute this through the instrument, how we will do this? So, this is basic instrument for this and we call it particle size analyzer. Here particles are fed from a sample funnel into the measurement area by vibrating feeder. Now, if you see this, here we have the funnel and this is the vibrating feeder. Once the feed is coming to the funnel, it drops in this feeder, it vibrates. So, due to that vibration, material is continuously fall between the analyzer. So, here you see this is the funnel and this is the vibrating feeder, material is continuously fall in the analyzer. Now, here if you see this particular section, this is called strobe and here we have the video camera. This continuously takes the picture of this as particles falling in between these two. So, sample particles are dropped between a video camera and the synchronized strobe light by a vibrating feeder. When the strobe flashes, the camera takes the image of the particle and this image are displayed on the associated computer and the picture is then analyzed by the software. So, if you see this particular image which is reflected on computer screen, this is basically the pictures taken by this video camera. So, after a short interval continuously these images are coming and we can analyze this. How we can analyze this? It is shown in this slide. So, if you see this particular image where a single particle is shown, which we call a digital image. So, a digital image is made up of uniform size pixels. If you see these square or rectangular shape cells, these are called the pixel which are of uniform size. By counting the number of pixels in each particle, the size and shape of particle can be determined. If I consider the diameter on this axis, you can simply count, this is 1, 2, 3, 4, 5 and similarly up to 15 we can calculate in this, we can count in this. So, if you consider the largest diameter, it will have the value equal to 15. So, using this image, particles are measured for area, periphery and minimum and maximum diameter. From these measurements, shape factor and particle volumes are computed. Thousands of particles can be measured in each digital image, and images can be taken at up to 20 frames per second. So, total sample analysis time is generally 3 to 5 minutes. So, this is the method how we measure the particle size as well as shape using the analytical instruments. Now, in this particular lecture, I will demonstrate a worked example. Here I have the problem. Following is the result of a screen analysis of pyrite having the specific gravity as 5. So, if you see this table, here we have represented the data which we have got from the screen analysis, which includes mesh number from 4 to 200 and screen opening from 4760 to 75. So, here if you see this mesh number, here we have used the American standard, then the Indian standard screen, and mass retained on each screen is also shown over here. So, what we have to compute for this problem? The first is the specific surface area. Secondly, we will compute number of particles if all particles are of a spherical shape. So, here we have to consider the uniform shape of particle, that is spherical. Third, we have to calculate quadratic mean diameter, and finally, we will compute Sauter diameter for the mixture. Now, to calculate the specific surface area or number of particle or quadratic mean dia, first of all we have to calculate the average diameter of the particle in a particular fraction. For calculation of average diameter, we should know from which screen material is passed and to which screen it is retained. So, if I consider the first one, here I am having -4 plus 6, it means material which is passed from 4th screen and retained on 6th screen is basically 30 gram. If you remember the previous slide, here what we have the value correspond to 4, we have 0 mass retained, it means nothing is retained on 4th mesh screen. So, whatever is passed from 4th screen is retained on 6th screen is equal to 30 gram. So, same we have represented over here, that is -4 plus 6. If I consider screen opening, that is -4760 plus 3353 micrometer. This we have shown, and corresponding to this we have the mass fraction equal to 30 gram, and similarly we can show for rest of the fraction in minus plus format to compute the average diameter of particles in each fraction. And I hope you are understanding what is minus, what is plus. Minus shows whatever is the undersized to 4 and plus shows whatever is the oversized. Here if you see this -4 and plus 6, in other word we can say -4 is basically showing the undersized to 4, it means whatever is passed through 4, and plus 6 is basically showing the material which is larger than correspond to 6 mesh number opening. So, -4 is basically undersized to 4, plus 6 is basically oversized to 6. So, minus plus we also call it undersize as well as oversize format. Now, we will compute specific surface area. To calculate specific surface area, this is the expression of specific surface area, where the expression goes as 6 by rho summation I equal to 1 to f ni xi by d average I. So, all these parameter we will consider, we will compute one by one, and then we will calculate the specific surface area. First of all, we will concentrate on mass fraction. So, total mass, if you count the mass retained on each screen, if you count all these value, it will be equal to 550 gram. For first interval, that is -4 plus 6, it has mass retained as 30. So, mass fraction for first interval is 30 divided by 550 equal to 0.5455. So, we can write the value of mass fraction of first interval here. In the similar line, I can calculate mass fraction for other fractions also. For example, -20 plus 28, it has 70, 70 divided by 550. So, the value comes as it is shown over here. So, if you join all this, if you add all these mass fraction, it would be equal to 1. So, here I have calculated mass fraction correspond to all fractions, and in this slide we have to calculate D average. For first interval, how we can compute the D average? The arithmetic mean of screen opening of 4 and 6 mesh number screens. So, it would be 4760 plus 3353 divided by 2. So, there is 4056.5 micrometer. In terms of meter, we can represent this as 0.004057, and this value we can write over here. So, here if you see this expression for specific surface xi and d average I for all fraction we have computed and we have written in this table. Further, we have to calculate the value of Ni, that is specific surface ratio. Now, if you remember this specific surface ratio for different material, we can see this value through a standard graph, and here I am having that graph which is plotted between ratio of a specific surface, that is n, versus average particle size diameter, that is in microns. So, if you remember the material, we have the material as pyrite, which is shown by 2 number plot in this graph. So, first value is 4057 micrometer, the average particle diameter. So, correspond to 4057, we can place a line, and correspond to this value as well as 2 number plot, we can calculate the, we can see the value of n from this graph, which comes as 5.2. So, you can see that using this graph we can calculate, we can find the value of n, that is a specific surface ratio, very easily, and similarly we can write the n value for other fractions also. Now, I am having all values to calculate a specific surface ratio. We already know the value of rho, that is the density, because we have given specific gravity of the material. Therefore, if you see this expression, we have to make the summation of Ni xi over d average I for all fraction, where I vary from 1 to f. If I am having all fractions as f, we can simply compute this, because we have already computed n, x and d average for individual fractions. So, for first interval we can calculate Ni xi and d average I as 5.2 into 0.0545 divided by 0.004057, and value comes at 69.9215. This we can write in this cell. In the similar line, we can calculate the value in rest of the fractions, and total summation of this would, we can simply add all these value of Ni xi over d average I, which comes as 4686.356 per meter, and density of the material is 5000. So, I am having all values, we can simply calculate specific surface area of mixture, that is 6 divided by 5000, which is the density of the material, into total Ni xi over d average I for all fractions. So, 5.6236 meter square per kg is the specific surface area of the mixture. Further, I have to calculate number of particles in a mixture. So, number of particles per kg we can write like this, capital N divided by capital M, and expression is 1 over rho A summation xi over d average I cube. So, first of all, we know d average for each fraction, we have to compute d average I cube for each fraction. The first interval, d average 1 cube value is coming as it is shown over here, which we can write at the proper place in the table, and similarly d average I cube for rest of the fraction can be computed. We have already computed mass fraction for specific surface area computation, so that we can use over here. So, now we have to calculate xi and d average I cube for each interval. For first interval, we can write x1 divided by d average 1 cube, and whatever value we are having is 817154.4014. This value we can write over here, and similarly we can write value in rest of the intervals. As we have summation over here, so this we have to add all the value of xi and d average I cube we have to add. The value comes like this, such a huge value, and density I am having 5000 kg per meter cube. I am having all particles of spherical shape. The value of A should be pi by 6. So, it comes as 0.5236. So, putting all the value over here, we can have 21242806 particles per kg. So, using particle size distribution data, we can calculate specific surface area and number of particles in the mixture. In continuation to this, we can calculate quadratic mean diameter, which we also call surface mean diameter. So, that is dq, and the expression goes as xi by d average I summation I 1 to f divided by xi d average I cube summation I 1 to f, and the whole is power 1 over 2. So, this is the expression. In the previous slide, for computation of number of particle, we have already calculated xi and d average I cube, which we have shown in this column. Now we have to compute xi d average I. For first interval, x1 d average 1 we have computed using mass fraction as well as d average value, and the value comes as 13.44643, and we can write the value over here. Similarly, we can write the value in rest of the columns also. Now, once I am having all values of xi d average I cube as well as xi over d average I for all fraction, we can simply sum them up to have the value of summation of these particular expression. So, xi over d average I cube give the value of 5561366741, and xi by d average I, it gives the value as 1777.305. So, using these two value, we can calculate quadratic mean diameter, and its value comes as 178.768 micrometer. In this way, we can calculate the mean particle size of a mixture. Please remember, this is the mean diameter or mean particle size of the mixture, not a particular fraction. Further, I can calculate Sauter diameter. We are having the expression dVs equal to 6 by rho Sm, where Sm is specific surface area, which we have just computed. Specific surface area means it is surface area per unit mass, and if you remember, Sauter diameter is the volume surface ratio. So, here we have to multiply Sm with rho to calculate the volume surface ratio. And if I put the expression for Sm over here, the final expression of Sauter diameter is 1 over summation Nixi over d average I. So, here in this slide we can write the value of Nixi by d average I, which we have computed once we were computing the specific surface area of the mixture. All these value we can find, we can have the summation of this, we can have 4686.356 per meter. So, considering this value, we can calculate Sauter diameter as 1 divided by this complete value, and Sauter diameter comes as 213.385 micrometer. So, in this way we can calculate the specific surface area, number of particles, quadratic mean dia, also we call as surface mean, and Sauter diameter we can calculate once I am having the particle size distribution data. So, that is all for this worked example. So, summary of this lecture goes as differential as well as cumulative particle size distribution was discussed once we are having screen analysis data. Secondly, in this lecture we have discussed the estimation of particle size and shape using measuring instrument, and finally we have solved one example, and we have computed the specific surface area, number of particle, mean size and Sauter diameter of the mixture, and that is all for this lecture 5. Thank you.